Welcome back to another edition of TEC 240. In this edition of TEC 240, we're going to be talking about voltage and current distributions through components that are connected either in series or in parallel. So what I have in mind for today, I've got three different concepts that I want to talk about. Over on the document cam, I'll shift over and talk through these three different things. And then after that, we'll briefly talk through Lab 2. You're going to do that in Tinkercad very similarly to the way that you did Lab 1. The only difference really is that you're going to be using the power supply in Tinkercad, and you're going to have to be using the multimeter not just to measure resistance, but also now to measure voltage drops and to measure current through those resistors that you're going to use in Lab 2. All right, so real quick though, before we get started with those three concepts that I want to talk about, I want you to do a quick thought experiment, or let's do a quick thought experiment together. And I hope I remember to come back to this at the very end of the video today. But here's a thought experiment, all right? So in my neighborhood, a very popular thing for people to do or to have are these giant trampolines that are, I mean, they might be, I don't know, a lot of them are 12, 15, maybe 20 feet across, something like that. They're really giant trampolines. I don't have one in my backyard because I'm sure they're expensive. And also, how are you gonna mow around that? That just seems like a pain in the butt to either have to trim around the legs of the trampoline, or else shove it out of the way so you can mow. I mean, we have a play set with a swing set for my kids in the backyard, and that's a big enough pain in the butt to trim around. So we don't have a trampoline. But anyway, so trampolines, I have noticed, are extremely popular in our neighborhood. If you go on Google Earth, you can see the same thing. But let's say that I had a house with a trampoline, and that trampoline happened to be located underneath a transmission line, overhead electric transmission line. All right, you can probably see where I'm going with this. So let's say I decided to have some fun one day, and I was jumping up and down on the trampolines, which are dangerous, by the way. I actually did when I was a kid. When I was in high school, I had a friend who was jumping on one of those trampolines, and a couple kids all jumping together on the trampoline. He got launched and fell down on his stomach and landed on like the side of the trampoline, the metal bar support, and ended up having to have emergency surgery on his, what was it? I want to say spleen. I'm not totally sure, but anyway, they can be dangerous. So make sure you keep the padding and stuff if you're going to use one of those. Anyway, let's say we're jumping on the trampoline up and down, and I get one of my friends to jump with me, and we time it just perfectly so that the other person is coming down just as I'm launching up, and you get one of those awesome jumps where you can go really high up into the air. And let's be kind of crazy, and let's say that I was able to jump like 20 feet up in the air, up to the transmission line, and I grab the transmission line. Now the thought experiment is, what happens next? What happens to you if you are unlucky or unwise, probably unwise enough to be able to jump up into a transmission line? Just one line, okay, that might come into play later. But let's say it's just one transmission line, single phase, so just your standard one wire, and so simplified transmission line. And one transmission line, I grab onto it like this, And the question is, do you die? Do you get shocked? Do you feel anything? What happens next? So think about that a little bit as we're talking through these things, and I'll try to come back to that, all right? Okay, so let me switch over now to the document cam. Okay, of these three things that I want to talk about today, one of them is really kind of a conceptual thing, and two of them are really just tools that you can use for doing some circuit analysis. So the first one we'll do is the kind of conceptual thing. So first of all, I'm going to draw a couple of circuits, and I'm going to draw a series circuit, and I'm going to draw a parallel circuit. And we're going to compare and contrast a couple of things between them, okay? So first of all, let's draw the series circuit with R1 and R2. And for our present purposes, it doesn't even matter what the values of R1 and R2 are. So we'll just leave it like that for right now. And then here's our parallel circuit. And likewise, it doesn't even matter what the values of R1 and R2 are. But what I want to talk about, this is the conceptual thing. What I want to talk about is the value of the voltage drop across R1 compared to the voltage drop across R2 in a series circuit, and the value of the voltage drop across R1 compared to the voltage drop across R2 in a parallel circuit. And I want to talk about the current flowing through R1 as compared to the current flowing through R2 in a series circuit, and the value of current flowing through R1 as compared to the value of current flowing through R2 in a parallel circuit. All right, so I'm going to write out kind of like a little table here. Let's write current for a series circuit and voltage drops. And remember, a voltage drop is the difference between the value of the voltage right here compared to ground and the voltage right here compared to ground. So how much did the voltage drop from here to here? All right, so the voltage drops of R1 as compared to R2. How do the voltage drops compare? V1 versus V2. Same thing over here. Current and voltage drops. Okay. All right, so this is the little table I want to fill in, and this is a conceptual thing that's really important to just know for you as you're going to be analyzing some of these more complicated circuits. All right, so the first thing is, well, where should we start? We could start anywhere we really want to. I'm not necessarily going to do this in any order. I'm going to go in kind of most to least intuitive, I think. So I think the most intuitive thing maybe to look at is to start here. We want to talk about the value of the current through R1 as compared to the value of the current through R2. All right, and so maybe you could already tell me that, but what I'm trying to convince you of is that they're going to be the same. All right, so imagine a unit of charge, whatever that unit of charge is. It's going to leave the voltage source from the positive side because we're talking about current flow, conventional current flow. And our unit of charge is going to come out of the positive side of the battery, and then it's going to flow through this wire. Just imagine if it helps that that wire is a pipe with fluid flowing through it. So you've got flow through this wire, or you can imagine it as a pipe if you want to, and that charge is flowing through this wire, and it's going to flow through resistor 1. But then it's not going to stop there, just like water flowing through a pipe doesn't just stop in the middle of the pipe. It has to keep going through the circuit, and there's nowhere else for it to go. It's not like the charge can just stop here. It's not like it's going to leak out. We're going to assume that we don't have a leaky piping system. We don't have leaky wires. I'm not even sure how that would really happen. But your charge is going to keep on flowing through here. And whatever charge or whatever current is flowing through this resistor has no choice but to keep on flowing through the circuit, and that same amount of charge has to flow, which is current. That same current has to also flow through resistor 2. So what I'm trying to convince you of is that the current through R1 is the exact same as the current through R2. It has to be. There's no other place for the charge to go as it's flowing around this complete circuit. So whenever you have a series circuit, the current through any components that are in series has to be the same. You can almost define that as a definition. You can almost say that's a definition of a series circuit. Two components are in series if whatever current flows through one component has to also flow through the other component. That's a pretty good definition of a series circuit, actually. So the current flow through components that are wired in series is the same. It has to be. So the reason why this is really useful for you to know is because let's say you're analyzing a much more complicated circuit than this. Just look at some of the circuits in Lab 3 and you'll see what I mean. If you can figure out the current flow through one resistor and it's wired in series to another resistor, then immediately, without even doing any calculation, you know what the current flow through that other resistor is. That's why it's useful. Okay, and that will come into play, I promise you. And not that long, in just a couple of labs, you're going to find that very useful. All right, so hopefully I've convinced you of that part. All right, the next, I think, most intuitive, is to look at this. To look at the voltage drops across components that are wired in parallel. And here's, I think, the easiest way for me to convince you of what I'm about to tell you. Here's a multimeter, as I'm kicking the table. Here's a multimeter. Let's say that I set it to measure the voltage. And here are my voltage probes. All right. Now, if I take my probes of my multimeter, and for the moment, let's just say it's a 12-volt battery. It doesn't matter, but let's just say it's a 12-volt battery. All right. And if I'm going to put the leads of my probe, one right here on the negative side, and one right here on the positive side of the battery, and if it's a 12-volt battery, what am I going to read on my multimeter? Hopefully, I read 12 volts, or pretty close to it, right? If you've worked a lot with 12-volt batteries, you probably know that when they're fully charged, they're not actually 12 volts. When you have a fully charged 12-volt battery, it's actually more like close to 13 volts, maybe 12.8, 13.1, something like that. So anyway, that's beyond the scope of what I'm talking about right now. But if it's a 12-volt battery, it's going to be about 12 volts. Let's just say it's 12 volts right now. All right. Hopefully you believe me on that. Now the next thing I can do is, let's just say I move my voltage probe just a little bit, like to here, and this one just up to here. All right. Now what voltage am I going to read on my multimeter? Well, all I've done is move it a little bit along this wire. And for most practical purposes, especially in this class, we're going to assume that wire has zero resistance. We're going to just make that assumption. And it's a pretty decent assumption for most practical cases. If you extend that to an extreme, like a transmission line, then no. A transmission line does not have zero resistance. You can't even really assume that. It's a bad assumption. But for our little tabletop circuits, that's a pretty good assumption. So if the wire has zero resistance, then it has no voltage drop. All right? So we do not drop voltage. The voltage does not change as we're just going along a wire. Okay? Why? Because of Ohm's law, V equals IR, and if R is zero, then V is zero. So I'm not dropping any voltage as I move my probes along the wire. All right? So hopefully that makes sense to you. And now if I ask you, what's the voltage I would measure here? hopefully you would agree that it's still 12 volts. And if I move these wires, probes over here, hopefully you would still agree it's still 12 volts because I haven't dropped any voltage along these wires. And now let me go all the way over to here, to this side of this resistor and this side of this resistor. And guess what? It hasn't changed. I still have a voltage gain from the black to the red, or more commonly for a load, we'll say we have a voltage drop from the red to the black. We have a voltage drop for loads. We have a voltage gain for voltage sources. So for these loads that we're talking about, I have a voltage drop from here to here of 12 volts because I haven't dropped any voltage anywhere else in this part of the circuit. So from here to here, it's 12 volts, just like it was at the source. And similarly, if I go all the way over here and I measure from here to here, it's also 12 volts. And I can have an infinite number of resistors in parallel, and the voltage drop across each one of them would still be 12 volts, no matter how many I have. So what we can say is that if we have voltage drops, if we have components in parallel, then we can say the voltage drops are always going to be the same. Well, whatever it is, if it's a 9-volt battery, a 12-volt battery, or it's a 120 volts, whatever it is, but they're always going to be the same. Okay, so I think those are both pretty intuitive. The next ones might not be quite so intuitive, but still not too bad. All right, so let's talk about maybe this one next. Let's talk about the voltage drops for components that are in series. All right, so we already know this, so let's use this, okay? The current I1 has to be the same as the current I2. All right, and we're trying to say, what's the voltage drops? What's V1 in comparison to V2? The voltage drop from here to here as compared to the voltage drop from here to here. And all I want to say here is it going to be the same, maybe, or is it going to be potentially different? Those are my two options, all right? So I think I can convince you of this, even if you've never seen anything like this before. We know Ohm's law, right? That's actually going to be one thing we'll talk about later on. We know Ohm's law, V equals IR. So we have V1 equals I1R1, and we have V2 equals I2R2. We know that I1 equals I2, but there's nothing that says that R1 has to equal R2. I can put whatever resistances I want here, right? And if I have different resistances here, then my R's, I'll go ahead and write it out. Maybe it'll be R1, V2 equals I2, R2. That's a 1. V1 equals I1, R1. V2 equals I2, R2. These, I1 and I2, have to be the same. We said that, right? There's nothing that says that R1 has to be equal to R2. I can put whatever resistance values I want in there. And if I put a resistor R1 that's different than the value of the resistance R2, then V1 is going to be different than V2. It just depends on the resistance values, right? So if R1 happened to equal R2, then sure, V1 would equal V2. But in most cases, probably more likely and generically, R1 doesn't equal R2, and therefore V1 is potentially different from V2. So all I'm going to write here is potentially different. It depends on the relative values of R1 and R2. All right. Okay, so hopefully you're with me on that. The last one here is, let's talk about the current flowing through R1 versus the current flowing through R2. This one actually is probably pretty intuitive. Again, there's nothing that says that R1 has to be the same as R2, right? And I think it's probably pretty intuitive that if, let's say, R1 is much bigger than R2, that means R1 is going to have a much larger restriction to flow, right? That's what resistance is. It's a restriction to flow. So R1, since it has a much larger restriction to flow, it's going to end up having less flow, right? That kind of makes sense. So if R1 is much larger than R2, you're going to end up having a lot less flow or current through this branch than you have through this branch. If R2 is much smaller, that's less resistance, less restriction, and so most of the current will end up flowing through this route instead of this route. All right, so we don't even have to put numbers in there. I don't even think we need to write the equation or anything here. I think that it's fairly intuitive that we could say that this current is potentially different, once again, depending on the relative values of R1 and R2. If R1 happens to equal R2 in that special case, then sure, the current is going to be the same through these. But if one of these is larger, then whichever one is larger is going to have lower flow, lower current, and whichever one's smaller is going to have more current flowing through that branch. Okay? All right, so these are just really important and helpful concepts that you should have in mind, because when we get to doing more complicated circuit analysis, you can use these and they'll be really helpful. Trust me, they will. If you just know these like the back of your hand, then you will have to do less calculation, because some things you can just, you'll just know it. You know, after you solve for something else, you'll just know it. For example, if through some other means I was able to calculate the voltage drop V1, then automatically I would know, if I was trying to calculate it, I would automatically know the value of V2. And I would also know the value of the voltage source if I didn't know that yet. So it just comes in really handy if you just know these different concepts. So that's concept number 1 for today. Okay, concept number 2. Let me go ahead and flip to a new page. Concept number 2, which should we talk about next? Let's talk about the one that this one you probably haven't seen before, I'm guessing. And this one is called the voltage divider. It's just a tool. It's just a circuit analysis tool that comes in handy sometimes. It actually comes in handy in circuit design sometimes, because let's say for whatever reason you need a 9-volt voltage source, but you don't have a 9-volt battery. All you have is a 12-volt battery. Well, you can actually design a circuit that you can get 9 volts from that 12-volt battery. And here's how you're going to do it. I'll show you how to do it. So here's a little example here. Let's have this circuit. This actually builds up what we just talked about. Let's say we have R1, and let's say we have R2, and that's it. We'll just keep it simple. R1 and R2. And we just kind of talked about this. So I want to know the value of V1. We're talking about voltage now. What's the value of V1 as compared to the value of V2? What's the voltage drop across here as compared to the voltage drop across here? All right, so you can't tell me it right now for a number of reasons. I haven't even told you what the voltage source is, and we don't know, probably more importantly, we don't know what the relative values of R1 and R2 are, right? Because I'm asking right now about the value of the voltage drop. So let's just say V, I'm going to go ahead and write this down. The voltage drop across resistor or component in is equal to I in R in. Yeah, that's not supposed to be a 2, it's supposed to be an in. I in R in. All right, so maybe we could get the value of I in if we knew what these were, and we could calculate R total. And maybe if I knew that, we could calculate this. But it still depends on the values of R1 and R2, right? But I think even so, I think it's still intuitive that you could say, all right, if R1 equals R2, if these two resistors are equal, then they're going to have the same voltage drop, right? because you know they're going to have the same current through here, so I is going to be the same. And if R1 equals R2, if these are the same, then I could plug those in here, and R is going to be the same, so I would have the same V. I'd have the same voltage drop. All right, so hopefully you believe me, and hopefully you get it, that if R1 equals R2, then they're going to have the same equal voltage drop. And furthermore, that voltage drop will be half of whatever the value of the voltage source is. If this is 12 volts, and if these two are equal, then I'm going to have 6 volts dropped from here to here, and 6 volts dropped from here to here. All right, so that's kind of the first step. The next thing, let's say now, I'm still just doing this qualitatively. I'll put an equation with it in a minute. But let's say that R1 was much larger than R2. All right, so R1 is a really big resistor, big resistance. R2 is a really low, small resistance. All right, so if you plug those in over here, just kind of think about how these would plug in over here. If R1 is much bigger, and again, they have the same current because they're in series, they have to have the same current. If R1 is a lot bigger, then V1 is going to be a lot bigger than V2. Because when I plug those R's in, if R1 is going to be much larger, that's going to force V1 to be much larger than V2. All right, so whichever one has the larger resistance is going to have the larger voltage drop. All right, so we can actually put, this is actually kind of a law, and we can actually put this into an equation. In general, this is not quite the equation yet, but we could say the voltage drop across a component is proportional to, this is kind of what we just said, it's proportional to the resistance of that component. So the voltage drop across resistor 1 is proportional to the resistance of resistor 1 compared to, or as a fraction of, R total. So if R1 is big as compared to R total, then the voltage drop across resistor 1 is going to be big. If the value of resistance 2 is small in comparison to R total, then the voltage drop across resistor 2 is going to be small. All right, so that's just kind of the qualitative thing that we just went through. And we can put this into an equation that is useful. I'm going to write it like this. The voltage drop across resistor in, so yeah, that's a subscript with a subscript, but no big deal. It's the voltage drop across resistor in is equal to the product, I'm going to go ahead and write this out. It's equal to V total times this ratio of the resistance of component in divided by R total. All right, so that is known as the voltage divider equation. The voltage divider equation. Because all we're doing is we're just dividing up the voltage. We're kind of apportioning the voltage as a proportion of its resistance compared to the total resistance in the circuit. Okay, let's do an example just to make it more concrete. Let's say that, let's make the numbers really easy, okay? So probably won't even have to use a calculator. Let's say that this is 10 volts, and let's say that R1 is 500 ohms, and let's say that R2 equals 100 ohms. We'll make them pretty different, so it's pretty obvious what's going on. All right, so first we're going to need to know R total. They're in series, so R total equals R1 plus R2. 500 ohms plus 100 ohms is 600 ohms. All right, and that's all the work I have to do before plugging into this equation. So let's go ahead and find V1. And I could calculate V1 by plugging into this equation. So V total is 10 volts times this ratio right here. R in, well, in is equal to 1 because we're trying to find the voltage drop across resistor 1. So R1 is 500 ohms. 500 ohms divided by 600 ohms. Okay, well, I did not succeed in making it so we don't have to use the calculator. I got to use the calculator for this because I don't remember what 5/6 is. So this is just 5/6, right? Or 500/600. So your ohms cancel out, and so do your hundreds. So all we have here is 10 times 5 divided by 6. Make sure you got the parentheses there. 10 times 5/6, okay? 10 times 5/6 gives you 8.33. Let's go out to the millivolts. All right, so 8.333 volts. That's close enough. All right, so it's pretty straightforward, right? Let's do one more just to make sure everyone's clear on this. Let's go ahead and do V2. V2 equals equals the product of V total, which is 10 volts, times now N equals 2. So the value of R2 is 100 ohms. The value of R total is still 600 ohms. So once again, your ohms cancel out, your hundreds cancel out, and you're left with the product of 10 times, parentheses, 1/6, or 100/600. 1/6. And that gives me 1.667. We'll round to the nearest millivolt. 1.667 volts. All right, so there it is. That is the voltage divider. And it's pretty useful in real life. Like I said, if you happen to have a voltage source at 1 voltage, but for whatever reason you need a voltage source at a different voltage, then it's not that big a deal to just, get a couple of resistors and build a voltage divider. It's pretty easy. Okay, the last concept is actually really easy. All it is, it's a tool. Just like voltage divider is a tool. You've all seen this before. Ohm's law. That's all I wanted to mention. Ohm's law is the third one. It's just a tool. It's one of lots of different tools. It's not a particularly powerful tool because there are plenty of cases, and you're going to see this in the very next lab, lab 3. You're going to see where there are cases where Ohm's law is not enough. You're going to need some other tool. But for lots of cases, Ohm's law works just fine. It allows you to solve the problem. So, yeah, we already talked about this. You can remember it however you want. Some people like to draw a triangle, and they put V and I and R, and then cover up whichever one you're wanting to solve for. Or, like I said last time, you can just remember V equals IR. But here's what I'm going to tell you. Here is my strong recommendation. Is that, I may have said this last time too, I don't remember, I really don't remember. I'm going to tell you, don't write it like this. Don't write it, or like that for that matter. When you're writing it out in the course of solving something, don't write V equals IR. Use subscripts, right? V, for example, V1 equals I1 R1, or V2 equals I2 R2. Or if you're solving for the voltage of the voltage source or the total, write out V total equals I total R total. It's just that I've taught this course a few times, like I said last week, and I've seen this become very confusing when you only write it like this. If you only write it like this, and if you've got 6 different resistors that you're trying to solve for, then it becomes very confusing, and you don't remember which voltage you solved for, you don't know which current you solved for. It becomes very confusing. So be specific. That's the reason why I'm talking about this right now, is be specific to the component that you're talking about. All right. Yeah. I think I'll just leave it at that. You can, with the combination of this and the voltage divider and the knowledge that I talked about earlier with this, then you can solve a lot of calculations. I feel like I want to do one more example. So it might be helpful. I don't, there's a balancing act here that I'm trying to balance between. I don't want to make these videos too long, but also, it's hard for you to ask questions, and so I want to err on the side of giving plenty of examples. So I think I might want to just do one more example. So let's go ahead and do that. All right. So I'm just making this up on the fly. Let's say that I've got a 12-volt supply, voltage supply, and let's say that I've got R1, which is equal to 100 ohms, and let's say I've got R2, which is equal to 200 ohms. And let's say over here, let's just do this. We don't need to make it too complicated. Let's say we've got R3, and I think I'm going to say this one is, let's say this one is, I don't know, 600 ohms. Okay, just for fun, all right? All right, so here's what we've got. Here's our circuit, and I want to calculate I1 and I2 and I3 and I total, which would be the total current coming from the voltage source. And I want to know V1 and V2 and V3 and V total. Okay. All right, that'll work. All right, so the first thing that we've got to do when we look at this is we've got to simplify this circuit. All right, so we can't calculate a whole lot. Actually, there's some stuff that we could do. One thing I kind of think is fun about these types of problems is that there's almost always several different ways to do it. So I can actually tell you right now there are several different ways that I could do this problem. But I think the first thing I'm going to do is I'm going to combine these resistances into a total resistance. That's probably the way you are used to doing it. So here's what I'm going to do. First of all, I'm going to look for how can I combine these. Well, I can't combine all of them right away because I don't have an equation for combining all three of these, because these two are in series. And then the two of these combined are in parallel with R3, right? So first I'm going to combine R1 and R2. And I'm going to do that by combining these, and I'm going to call that R equivalent 1. And I can solve that pretty easily. R equivalent 1, can you see that? R equivalent 1 equals R1 plus R2. R1 is 100 ohms, R2 is 200 ohms, so R equivalent 1 equals 300 ohms. All right, and now you can actually redraw this circuit because we just simplified it. So now that circuit becomes something simpler. And it looks like this. Now I've got R equivalent 1, and that is 300 ohms. And I've got R3 still, haven't done anything with that yet, and that's 600 ohms. All right, so this is my new circuit that I just simplified from that circuit. And now what I can do, still got to combine these. So now I can combine these, because they're in parallel, and this will just be, I could call it R equivalent too, but this is the last step of simplification, so this is just going to be R total. All right, so I can do that. 1 over R total equals 1 over R equivalent 1 plus 1 over R3. All right, now we've seen this a bunch of times before. So 1 over R total equals 1 over, that is 300 ohms. And that is, R3 is 600 ohms. All right, so remember we're going to take the inverse of both sides. Okay, so be careful when you plug this into your calculator. All right, so first I'm going to do what's inside the parentheses. So I'm going to do 1 divided by 300 plus 1 divided by 600. Oops, I'm going to use parentheses here. 1 divided by 600. There we go. That's what's inside the parentheses. Now I got to take the inverse of both sides, so take 1 divided by that. And there we go. Actually, that works out to a pretty nice even number, doesn't it? 200 ohms. So on the left side here, 1 over R total is just R total. So R total is, what we just did, was 200 ohms. Okay, good. That's great. That's not directly asked for up here, but that's probably most of the work in the problem. So I'd say we're at least halfway there, actually. All right, so R total, we know R total, and oh yeah, we know V total. In fact, we can go ahead and write that in. V total is just the voltage of the source, the battery, so we can write that in. So now that we know V total and R total, we can find I total. We're using Ohm's law for that, and we can write I total equals V total divided by R total. That's just rearranging Ohm's law. V total was 12 volts and R total was 200 ohms. And 12 divided by 200 gives me 0.06 amps. Because when you take volts divided by ohms, you get amps. Okay, so now I got I total. I can plug that in right up here. 0.06 amps. All right, so what should I do next? Well, you know, the most intuitive thing to me to do next is to say, well, I know V total here, and guess what? R equivalent 1 is in parallel with R3, and I know the voltage drops for both of those. So I don't necessarily care about the voltage drop across R equivalent 1. That doesn't really get me anything directly, but this does. I know the voltage drop across R3. In other words, I know V3. All right, so since it's in parallel, this is like the thing with the multimeter probes where I went like this, and I can say that if it's 12 volts here, then it's 12 volts here, because I don't drop any voltage along the wires. So I know what V3 is. It's just 12 volts. And now I know R3, and I just wrote in V3, so I can go ahead and solve for I3. I3 equals V3 divided by R3 equals 12 volts divided by 600 ohms. It's going to be a pretty small number. 12 divided by 600 gives me 0.02 amps. Okay, so I3 is 0.02 amps. All right, now we've got everything that we need to know about component 3, resistor 3, and about the total voltage, total current. What we have left are these two right here. All right. So there's several different ways that I can think to do this, but I think I'm going to use a concept that we just talked about, and that is the voltage divider, because it's applicable here, right? So it's applicable because I know the values of these resistances, and I know the voltage drop across this branch, right? So these are in series, so I can use voltage divider, and I know these resistances, and I know the voltage drop from here to here. It's the same as V3, and it's the same as the voltage source, right? These are in parallel. So I know what V total is. V total is the voltage drop across here from here to here, and it's just 12 volts. And so now I can use voltage divider to find V1 and V2, right? So if you remember, here's our equation for voltage divider. So let's do resistor 1 first. So we'll go ahead and plug it in. So the voltage drop across resistor 1 is going to equal V total times the value of resistor 1 divided by R total. Be careful here, though, because this is only for that series branch that we're talking about right now. Okay, so be a little bit careful here. Up here, you know, we only had this in series. We didn't have this other resistor over here. So in R total right here, my R total, when I apply it to this problem, it's going to be 300 ohms. Okay, because we're only dealing with this branch right now. Okay, so let's do it. V1 is equal to V total, which is the voltage drop across this branch, which is 12 volts, times the ratio of R1, which is 100 ohms, divided by R total. Remember, that's just the resistance across this branch, because that's all we're looking at right now. So this branch has a resistance of R equivalent 1, which was 300 ohms. 300 ohms. So what we're looking at is 1/3 of 12 volts, because our ohms cancel out, our hundreds cancel out, and if my math is correct, 1/3 of 12 volts is 4 volts, right? Trust but verify. You ever heard that? 12 times 1/3. Yeah, okay. 1/3 of 12 is 4, so I'm left with 4 volts. So V1 is 4 volts. And now I know V1, I know R1, so I can get I1. So I1 equals V1 divided by R1 equals 4 volts. That was V1. Divided by R1 is 100 ohms. Oh, this is going to be real small too. 4 divided by 100. That gives me 0.04 amps. So let's write that in. I1 is 0.04 amps. And now this will be a good test because we know that I1 should equal I2, right? So in fact, I could just write that in right here. I really could. And what I just told you is that you can. And you can. If you have solved for I1, then you can just go ahead and write in I2 as being the same as I1, right? Because they're in series. But I'm going to go ahead and do it the long way because I want to double check myself. All right, so let's also get some more practice with voltage divider. So once again, I'm going to use voltage divider to get V2. So here's the equation for voltage divider. There's my V total across that branch. Now my N equals 2, so R sub N is going to equal 200 volts divided by R total for this branch, once again, is 300 volts. So now, ohms, not volts. These are resistances. So 200 ohms divided by 300 ohms. Your ohms cancel out. Your hundreds cancel out. You've got 2/3 of 12 volts, which is 8 volts. So V2 is 8 volts. And now we can use Ohm's law for I2. I2 equals V2 divided by R2. V2 is 8 volts that we just got. R2 is 200 ohms. And 8 divided by 200 gives me 0.04 amps. So we can breathe a sigh of relief because we must have done it right, because I1 is equal to I2, and they're in series, so it better be equal, or else I would have been a liar just a little bit ago when we wrote those conceptual things earlier. All right. So I hope I didn't belabor the point too much. This might be a bit of review for you. You might be bored with this, but I think it's better to risk that some of you might be a little bit bored than risk that some of you might be frustrated or confused because you're not quite following what's going on. So I think I'm going to stop this video here. We talked about 3 different concepts or circuit analysis tools that you can use in this video. In the next video, we're going to talk about Lab 2. And also, I haven't forgotten about the question about what happens if you jump up and grab onto a transmission line yet. So we'll talk about that as well in the next video. So I will see you there.